I am coming from the group that works with heterogeneous catalysis. Our main tool is DFT. Everything is pretty the same in all the projects. We are throwing some structures to WASP, some surfaces. We're not developing any quantum calculator. Still, just DFT by itself would be too boring. So I brought you two stories, one about electrochemistry and another about the big nanoparticles. And logically, I will start from the second one. Uh, Quite 7 years ago, our group published a paper where this was one of the pictures that tells us that you can attribute you can correlate the coordination number of each atom in your cluster with some energy. So you can look on the energy of each atom on different surfaces. So on 111 you would get coordination number 9, on 100 coordination number 8, and all these points would lie on one line with the second coordinate of the coordination number. Since then, for something like 5 years, we didn't touch this topic, and nobody actually else was interested in that stuff. And 1 year ago, we made the same story. The previous one was about platinum clusters. Here we have cobalt things. It's very same story. You can generate different surfaces and you will find the energy of atoms on the surface, and principally you can see these numbers as energy penalty for under coordination. So your bulk, your atom in the bulk in the FCC or in HCP as well, your atoms having 12 numbers, you are having no missing coordinations, and your atom is fully satisfied. However, on the surfaces, you would be less satisfied, or atoms would be less satisfied, and that would increase their relative energy. What to do with that stuff? Well, we can, for each atom of the cluster, we can easily calculate the coordination number. That is very primitive math. We can count how many of 6 coordinated atoms we have, how many 7 coordinated atoms we have, and we already know how much of penalty. Let's say we are getting 1 EV for two missing coordination numbers. So we can easily calculate some energy for a given particle. And then we can generate another particle, and for that particle we would also get some coordination numbers that would actually be different, and energy of such particle also would be different. What to do with that? We can go to a Monte Carlo algorithm. I won't go into details. I assume that everyone more or less knows what Monte Carlo algorithm is doing. And we can take some bigger nanoparticle. We can throw it into Monte Carlo and look what Monte Carlo would do with it, trying to minimize energy. And as you can see, it's slowly getting some shape. We can, well, of course, we are starting from a higher temperature, then temperature dropping down. The higher temperature at the beginning, we need just to overcome some unfavorable minimas, and then we are getting to a pretty good shape. How big structures can we work with? Well, we have example of 47,000 atoms. Actually, I can such a 3D print that would be a cobalt particle of 10 nanometer with 47,000 atoms. Well, how you can see that it's very cheap. How accurate is this approach? We cannot calculate on DFT 47,000 atoms, but we can look on something like 100 atoms, 200 atoms, 400 atoms clusters. You can see that Monte Carlo calculated values, they are well determined. This is actually corresponds to a minimal or double of the minimal energy penalty that you are getting for replacement. And you can see that for 100 atoms, you are having still quite a deviation from DFT numbers. You are having 2.6 milli-electron volts. We are actually at the moment now looking how bad it can go with the smaller clusters. But if you go other direction, if you go to a bigger clusters, your error dropping down. What does it give to us? Well, we can compare our Monte Carlo crystal with Wolf construction that is normally used for such things. Your Wolf construction would predict you on the atomistic level something of this shape. But Monte Carlo, that is closer actually to reality, gives you much more defects. That's still, however, that's not the Yevgeny's picture, that's another spherical cow, but we are still having the nanoparticle in vacuum without support. That is not that much of any practical use. Well, we can easily integrate support into stories. So on one side of our nanoparticle, we will, except of the penalty of being under-coordinated, we will include some benefit of being on the surface that is directly connected to the adsorption energy. Adsorption energy between, or interaction energy between cobalt and silica is easy to calculate on DFT. The same we did on other supports. And then we are getting quite clear decrease of height or decrease of height to diameter ratio that is very much beloved by synchrotron scientists. What else can we do? We can look on the effect of gases. For example, we can calculate the CO adsorption on different surfaces, include that into our model. That will obviously decrease the energy penalty, and then we can having new values. We can run this simulation once again, and we will see how the shape of the particle changes by applying some pressure of CO. You see that 111 surface decreases, 100 surface decreases even more. You get more and more of other surfaces that are previously not even discussed. And of course, we can see the effect of pressure of CO. But still, what is it giving to us? Well, it gives to us, for example, on this 8 nanometer particle, instead of very much beloved by Wolf construction 111 and 100, we are observing 13 different reaction sites, mainly on edges, and then we can calculate the reactivity of these sites. Specifically, we are interested on the CO dissociation. Very nice to present this work on the constructor with CO bond here. And we can find, first of all, we find that three lowest in energy, the most interesting, the lowest barriers, the most active sites that we found on the nanoparticles were not even ever considered for Fischer-Tropsch reaction on cobalt particles. Thus, we made a full circle and starting from DFT for making the model, we used the DFT at the end for the surface sites, for the reaction sites that we obtained by this model. What can I conclude from this part? First of all, I would like to advertise the code with which you can perform your simulation. That is extremely simple model and extremely cheap. It will allow you to work with 50,000 atoms with quite good accuracy. You are not limited to the choice of metal. You can include interaction with any support. You can by yourself change the values for gas phase effects and predict the active sites that were not known before. So far, the thing is for monometallic particles. We are looking if we will be able to extend it to bimetallics. I would like to thank to Tilman Gruger, who actually wrote the code that you are welcome to test, to Enrico Cereci, actually Dr. Enrico Cereci, who graduated 1.5 weeks ago, to my supervisor Felix Stut, to the Kerosene project that sponsored Enrico's PhD. And actually, these two people will be in the next part of my talk. Well, electrochemistry. 2 years ago, together with Evgeny and his student Alexander, not the Alexander who is here, but with another Alexander, we made a beautiful work related to ferrocenium electrode, to the not the experimental that majority of you know, but about making a computational ferrocenium electrode. We actually managed to predict the cyclic voltammogram for oxidation reduction of ferrocene, and the shape of this thing and the potentials fit quite well to the experiment. Of course, we didn't stop just on the ferrocene itself. We tried 2 dozens of different organic molecules for some of them, and all of them measured or simulated in respect to ferrocenium electrode experimentally and computationally. Sometimes it fit very well, sometimes it does not really fit, but that was the first simulation of this kind. If you are interested, you are welcome to download the code for such cyclovoltammogram simulations. And then we proceeded further. We used this computational ferrocenium electrode model together with Marcus theory for simulation of benzyl chloride turning or oxidizing electrochemical process, formation of the benzyl radical and interaction with CO2 molecules. We predicted normally what you can easily predict is this black line and the zero potential, but usage of ferrocenium electrode allows us to indicate what potential do you need to apply to get at least all the intermediates below the starting compound. It doesn't tell you that reaction obligatory will go, because calculation of transition steps is challenged by itself, but at least this is a Norskov model that tells us that reaction can go because all the intermediates are not higher than the starting compound. We developed this stuff further within a pretty big work related to Schoner oxidation. Schoner oxidation is electrochemical reaction that is of high interest by the pharmaco industry that allows you to functionalize alpha position to amines, amides, and so on. It's quite well, the reaction is known for many years, but mechanism of it is not really clear. This mechanism, you can go through the reaction in very many ways. You can have electrochemical steps, so oxidize the molecule, then get the proton transfer, and another another oxidation step or electrochemical steps. And then another chemical step with proton transfer, or you can make jumps, including what we already heard today, proton-coupled electron transfer, where you simultaneously losing electron and proton, and still you have a variety of possibilities. Using our computational ferrocyan electrode and using Markov's hash theory, we can well describe this kind of reactions. And also we can not only predict the energy of intermediates, we can calculate the barriers. Not only barriers of chemical steps that are never an issue, but also barriers of electrochemical steps and set steps. For the beginning, I am showing you what you get from very normal DFT calculations, but that of very little interest. What we are interested is when you are pushing your intermediates to be below the starting material. For this, you need 1.5 volts in respect to the ferrocyan electrode, but this is still not telling anything about barriers. Barriers are actually next step that requires Butler-Vollmer approach and Marcus-Hash approximation. You can calculate actually barriers for electrochemical and for set steps. For the here you start from the N4-methylpyrrolidine. You can get the final material would be methoxy N4-methylpyrrolidine that can be oxidized further to the byproduct that industry is not interested, but that is still can have a place. And our approach allows you to get the energies at each point of your process, at each potential. You can see how the barriers are changing, and you can also simulate both of oxidations separately or even simultaneously. So the solid line here is combination of two oxidation processes going sequentially. You can get the codes for doing that by yourself. How well it fits with experiment? I would say that experiment is of worse quality than what we can predict. We made simulation in methanol that is primarily used solvent in such oxidation. However, it's not favorable solvent because it oxidizes by itself, and we can account this oxidation in our model, or you can use fluoroethanol that is less prone to oxidation, and we predict the cyclovoltammograms in both of the cases, and I would say they fit quite well with experiment. This was oxidation in the bulk. We are looking as well on the processes on the electrode. For example, applying the problem in electrode processes is that quite often the simplest way to simulate the processes of on the surface on the electrode would be to add some specific amount of electrons, or to withdraw a specific number of electrons and look how it goes. However, you can, from the constant number of electrons, from the different structures, you might get different potentials. That's why we are actually now going from the constant charge approach to the constant potential approach. We are performing calculations of this system, calculating work potential, work functions, and seems I'm running slowly out of time. This approach using combination of DFT, computational ferrocyan electrode, Marcus Hash and Butler-Fulmer technologies, we can predict chemical, electrochemical, and Z barriers at specific potentials. The solvent effect can be treated explicitly as it was done for Schoner reaction, or implicitly what we are doing at the moment for the surface systems, and maybe not of the high computational cost, but sometimes beautiful just to add circular voltammograms to experiment, to compare with experiments. That work was performed with Alexander Kramarenko, with Dr. Tubiliana Savintseva. I would like to thank group leader Felix Stut to Electrification of Technical Organic Synthesis project that financed Liana by us, and of course to Dr. Evgeny Pitko for discussions and support, and of course to thank all of you for your attention.